In this video, we're going to study another gas law called Avogadro's law, and we're going to study a concept called molar volume. So let's go ahead and take a look at our little summary slide here. So you've already become familiar with Boyle's, Charles, Gay-Lussac's, and combined gas law. Today, we're going to focus on Avogadro's law. And then in another video, we're going to take a look at Dalton's partial pressure. So do make sure you review your Boyle, Gay-Lussac's, and Charles law to make sure you understand what variables you're looking at and how they're compared. You can see that in the previous video for gases and for gas laws. You can watch a great video about Avogadro's law over here, a nice preview of the material video to go over the concept with some demonstrations and excellent visuals. And we're going to go ahead and explore Avogadro's law now. So we'll read the definition together and then take a look at what all that means at a picture level. So at constant pressure and temperature, so your pressure and temperature aren't changing, the volume of the gas is directly related to the number of moles of gas, to the amount of gas as number of moles. So it's directly related to the number of moles of gas. So what that basically means is if you double your number of moles of gas, you double your volume. So the more moles of gas you have or particles of gas you have, the larger your volume is going to be, assuming you're at constant pressure and temperature. So for example, let's say at a certain temperature, I have 1 mole of gas, and the volume it occupies is 1 liter. Well, if I triple my volume, my moles of gas, then I triple my volume. So I have 3 times more moles, it takes up three times more space. And that's assuming I don't increase the pressure, I don't hold it down, that this will just basically increase the space that it takes up. So when pressure and temperature are constant, when they remain constant, equal volumes of gas are going to have the same number of entities. So what does that mean? That basically means that if I have the same pressure and the same temperature, if they're constant, nothing's changing. If I have 2 different samples, and those 2 different samples have the same volume, they have the same number of moles of gas or same number of molecules of gas. So for example, if I had a sample over here that was 1 liter and it contains 1 mole, and there's another sample that's also 1 liter, I can infer that that also contains 1 mole. That's another idea from Avogadro's law, that the volume is proportional to the number of moles or particles of gas present. So you can see this over here. This is our graphical representation of Avogadro's law. We have the amount of the substance or the moles of the substance or molecules of the substance in the volume here. So as you increase the amount of the substance present, the number of particles of gas, for example, we can see the volume goes up. So they're proportional to each other. So for example, over here, we have 1 mole occupies 22.4 liters. Now, if we double that, let's add some gas, let's double the number of moles, we've doubled our volume. So they're directly proportional to each other. Double moles, you double your volume. You had 22.4 liters here, now it's 44.8 liters. We keep our pressure the same though, so that piston would rise to make sure the pressure is the same. So we have 1 atmosphere on top, 1 atmosphere on top there as well. But the point is that you double moles, you therefore double volume. And that's how Avogadro's law can be represented. Mathematically, Avogadro's law is represented as volume 1 over moles 1 is equal to volume 2 over moles 2. So V1 over N1 is equal to V2 over N2. So let's take a look at how changing affects volume. So if you increase the number of moles or molecules of gas, you've increased your volume, and that's because you've added more particles of gas, and so there's more collisions, and so what happens is the volume has to increase to maintain the same pressure. If you decrease your molecules or moles of gas, your volume decreases. That's because there's fewer particles of gas, there's fewer collisions, and so your volume has to decrease to maintain that same pressure it had before. A great application of Avogadro's law is simply when you blow up a balloon or when you use a pump to put air into a ball. You're adding more particles of gas to the balloon or to the ball. And so you're affecting the volume by adding more particles of gas in. This is a great demonstration that goes over Avogadro's law. I do encourage you to watch it and to try to answer this question over here. So which of the reactions that these 2 individuals are doing will yield more gas molecules, and try to explain why that is. So go through the video and then try to think about why, or make a prediction and explain why you made that prediction. So let's go ahead and do some practice problems with Avogadro's law. And then after that, we're going to take a look at the molar volume. So the practice problem we'll do is example number 1 here. There are a couple things you should remember. So STP and SATP, just make sure you remember those as they will be important in some of your future calculations. All right, so let's go ahead and fill in some blanks. So we're studying Avogadro's law, which basically means that the number of moles of gas is related to the volume of the gas. And so we say at the constant pressure and temperature, the volume of gas is directly related to the number of moles of gas. So if you triple the number of moles, you triple the volume as well. So Avogadro's relationship is essentially that the volume is proportional to the number of moles. The moles is proportional to the number to the volume. So they're directly proportional to each other. As one goes up, the other goes up as well. So if you increase the number of moles, you increase the volume. And Avogadro's law can be expressed mathematically as V1 over N1 is equal to V2 over N2. So you have your volume for number of moles initially. And if you increase your number of moles, you'll have a new volume. Or if you decrease your number of moles, you'll have a new volume as well. And you can essentially isolate for the variable that you're looking for. Graphically, you can represent Avogadro's law as here's the amount of substance, let's say in moles or particles. As you increase it, the volume goes up as well. And then we saw that we tried to explain this law. So again, Avogadro's law, we're trying to see how increasing or decreasing number of moles will affect the volume. So if you increase the number of moles, the volume increases in order to try to maintain the pressure. Since you have more collisions due to more particles, the volume's gonna have to increase. So when we go from n is equal to 1 to n is equal to 2, so 1 mole to 2 moles, we doubled the number of moles and we doubled our volume. We doubled our volume to try to maintain that pressure. And then when you decrease the number of moles, well, your volume decreases. So it's just going the other way around. If you go from 2 moles to 1 mole, now your volume is lower. You have fewer particles there, fewer collisions, so your volume decreases to maintain that same pressure. So let's go ahead and see how we can apply this to a situation. So we have a balloon with a volume of 34.5 liters is filled with 3.2 moles of helium gas. To what volume will the balloon expand if another 8 grams of helium is added? Okay, so we're changing our volume. We're assuming that we're keeping the same pressure and temperature. We should have stated that. We'd have the same pressure and temperature. Our volume, our V1, so first I'm writing that all the information, is equal to 34.5 liters. And the number of moles to begin with is 3.2 moles. Now, what we're going to do is we're adding another 8 grams of helium. Okay, so be careful here. We need to find V2. We want to know what will our new volume be if we add more moles. We know the new volume should be larger. The problem is we don't know what our N2 is. So we need to find N2 first. We kind of told you, but not directly. So my step 2 is going to be to find N2. I need to do my 8 grams of helium plus the helium that's already there. So I need to somehow figure out how many moles of helium are in 8 grams. So if I want to do that, we know that my mass is equal to my moles times my molar mass. So my moles, whoops, let's erase that. My moles is going to be equal to mass over molar mass, which is 8.0 grams over the molar mass of helium, which we have as 4.00 grams per mole. Cross out grams, and we get about 2.0 moles of helium. So we are adding 2 moles of helium to our sample. Okay, so that means that N2 is going to be equal to 3.2 moles plus 2.0 moles, which will give us 5.2 moles. So now we'll have a total of 5.2 moles in our sample. Now, remember, Avogadro's law states that V1 over N1 is equal to V2 over N2. We want to find V2. So to do that, we can just send this to the other side. We get N2 V1 over N1 is equal to V2. So we can get that V2 is equal to, so N2 is 5.2 moles. And then the V1 is 34.5 liters. Make sure you're consistent with your volume. And the N1 is 3.2 moles. Or consistent with your units, I should say. So now we can cross moles out, we get liters. So we get 5.2 times 34.5 divided by 3.2. And we get about 56.0625 liters, which is approximately, we want to have 2 sig figs, so 56 liters is our V2. So by adding more moles, we've increased our volume. We went from, so therefore the new volume is approximately 56 liters, which makes sense because we added more moles. And that's what we said, that the assuming constant pressure and temperature, the more moles you have, the larger your volume should be. So let's go take a look to see if our answer is correct. So we can see if we're on the right track there. Here, about 56 liters is what we should end up with. And on our handout, you can see the application of Avogadro's law. I do want you to watch this video here so you can explain the application, how it works, and explain it with words and with a label diagram as well. So you can do that to finish off the application of Avogadro's law. We're going to continue with Avogadro's law in the next video, but we're going to go and explore a concept that's related to it called the molar volume, which is, again, connected to Avogadro's law.